Okay, well, so welcome to this mid-afternoon session. And so in the next 60 minutes, I think I try to talk a little bit about snow and how we can monitor it from space. And I will not focus on the optical one, so you heard this already all this morning. We are going now to the real stuff, looking for synthetic aperture radar, which is a little bit more complicated, and I think you might have a good background from the previous talks from Helmut and also from John on the different SAR systems, and also on some techniques like interferometry and so on. So very quickly on the contents of these next 60 minutes. So first I will show you some of the structural properties for alpine snow, focusing primarily on alpine snow. So we have seen it yesterday in real. So unfortunately, we didn't have the time to do some snow pits there. So it would have been an excellent exercise for everybody here. But I show you something what comes out after hard work, digging snow pits and measuring the snow properties. Then I quickly repeat some parts to fresh you up and update you on radar signal propagation in snow and ice. This will be the background then on the methods and on snow water equivalent and snow depth retrieval. And here I'm going through 4 different topics actually, which are currently under evaluation and research. Not everything works so far, but some of them are more mature, some of them are less mature. But I want to open some doors for your research in the next coming years, so maybe you are the one who have to solve these problems and make it operational in the next couple of years. We also don't have all satellite data in space so far, but they will come, so I'm sure. So the plan for the next 10 years, so you heard this from Espen and others, a lot of synthetic aperture radars are coming. And I provide you here now some of the techniques what we are currently working not only in NVO but also at other people in various projects. Okay, morphology of high alpine snow. I show you now 3 photographs and snow pits from a campaign what we had a couple of years ago in preparation of one of these snow water retrieval satellite missions. It was a candidate, it was not selected, what a pity. But anyhow, there was an extensive field campaign where we looked into the details and the interaction between radar and snow. And first I start with Rotmoos Valley. There it was a big site. You see this valley, it's a high alpine valley in the Ötztal. You can easily go there, you can even go up with the ski lift. The more fitter people walk up there with the skis. And then we have this typical high alpine valley with it's a flat terrain there. We have typical alpine tundra with some rocks, some vegetation below, so high alpine tundra vegetation. And of course there are these small riverbeds what you see here below the snowpack. When we look to this site, it was in February, mid of February 2013, you see one of these snow pits, what was measured actually by the people. So on the left side, you see the density, which is measured by a pole in principle, so every 10 centimeters. So to get in principle a stratigraphy and the density profile. This is important because radar is interacting with the crystals and of course the density and how this is backed is a measurement how dense the snow is. Then we are looking for the temperature profile, that's the red line here. And for every layer, on the other hand, we are estimating a couple of other parameters, more or less accurately, how good it is possible. One of the main one is of course, grain shape and grain size. And this is a tricky thing with radar, because we measure this, as you see here, with these grids. They have a certain size, 1 millimeter, 2 millimeters, depending on the snow what we are looking at. And then we estimate the size of the grains. We can do this also digitally. And then, of course, for coarser grains on the right side. And then we are looking also to the morphology, to the metamorphism of these grains. And I show you here 2 examples. This is a kind of melt freeze metamorphism. So these are these typical coarse rounded grains, they are sticking together, and microwaves interact with those very heavily, depending on the frequency, so the wavelength, and of course on the grains. Grains can be very small and they can be very big, as you see here. On the right side, we have these solid faceted particles, temperature gradient, which are growing in principle when we have strong temperature gradient. And this is the reason why we are measuring on the, in the snow pit also the temperature profile. Every 10 or 15 centimeters, every 20 centimeters, close to the ground in this case, we have 0 degrees. And caused by, because we have a thermal insulation, and the geothermal energy is actually going up and is heating up the ground snow interface. And then, of course, closer to the atmosphere, so to the snow ground interface, we are mainly influenced by the weather conditions, so by the snow. In this case, it was quite cold. But you can imagine that the temperature gradient of 10 degrees over this, how much is it, 1 meter 30 centimeters snowpack, is quite good. And this causes to have also water vapor gradients and so on in the snowpack, and this has a big influence on the grains and on the layering in the snowpack. In the same date, or almost the same date, a day later, we went up to Mittelbergferner. So this is winter snow on top of a frozen front. So this is a glacier close to Pitztal. You can go up with a ski lift and you walk 2 hours with the skis, and then you come to this high glacier plateau. We did a lot of measurements there, also snow pits and so on, and this is one snow pit of this. And of course we have a little bit more snow, so it's about 2 meters. And what you see also, when you remember just before to the density profile, we have a different density profile. Although it's measured more or less on the same day, so 1 day difference, different elevation, a slightly different location, so 10 kilometers more or less towards the west. And when we look also to the grains, they are of course different. So here you see some, so this is now bluish, very nice. So we know that it's done by Americans. So this field campaign, people from Boulder and so Kelly Elder and his team were joining. So we had 8 Americans doing the work for us, which was very nice, I have to say. Because digging snow pits is hard work, so you need strong people. Then another part, so this is now Leutasch. It is also on the 22nd of February, 13. 40 people were in the field measuring the campaigns. We had also airborne acquisitions during these campaigns. I show maybe some data later. And when you look now to the snow profile, it's totally different. We have really, it's at about 100, maybe some of you know Leutasch, it's very close to here. It is good for cross-country skiing, so there are the ski tracks for the Olympics and so on. Very nice to visit, I have to say. And when you go there for cross-country skiing, you can make a snow pit for us and then look to these properties. It is totally different what I have shown before. We have these very dense layers in the bottom. Actually, a few 10 days ago, before we did the measurements, it was very warm and we had rain on the snow, and therefore we had this very, very dense part. And when we look to the profile also of the temperature, it's also different. Grains are horrible, I would say. They are big, clustered and melted together because we had this water from the rain in this part. Just to see, we have 3 different sites in the Alps, close to each other, with totally different snowpack. It depends on the weather conditions, of course, on the elevation, on, not only on this, but also on the orientation towards the sun, away from the sun, and all the other parts. Even the ground below is very important. Not only how it is done, but also when or how were the ground conditions when the first snow was falling. Remember, on Monday we got fresh snow. Last week we had here in Innsbruck 30 degrees. You can imagine how the ground was, super warm. When this snow is not melting away, we will have a very thick ice layer finally on very close to the ground, which has a big impact on this part. So just remember, snow is not snow. Even on the same day, actually it will be very, very different. And all these factors have an impact on the interaction with microwaves, which makes it even more complicated. Microwaves are between a few millimeters wavelength up to 23 centimeters at L-band. They don't see the grains, what we see in the optical. They see it actually differently. They don't see the individual grains. They see the clusters depending on the wavelength. And this makes it really complicated. And when we go to the polarization differences, the shape of the grain, so you can model this as cylinders, as whatever, spheres, elliptical or whatever. But does it really be a mathematical model like this? The problem in these cases, we need a kind of model for these grain sizes in order to make an electrodynamical interaction between snow and the waves. We need to simplify this, and that's important. Penetration depth. Penetration depth, Helmut mentioned this. I will repeat it because it's quite important. This is now the one-way power penetration into different types of snow. But this is not modeled. This is based on measurements from different campaigns. So from Antarctica, from campaigns here in the Alps and so on, by different people. So it's Christian Metzler from University of Bern, actually one of the very big snow guys in the 80s and 90s. He did a lot of very, very good basic work. So if you read his habilitation, it's really recommended for this. You can find it, I think, even digital on the internet. It's a very good basic explanation of all his interactions. It was written in the 80s, but still it's a kind of Bible for me for interaction between snow and microwaves. Then Helmut did some measurements in Antarctica. And when you look here, so this is on the average, okay? So don't take into the truth, but it gives you some idea, in dependence on the wavelength, how deep we can look into the snow or what we are seeing. If a snow, for example, is 1 or 2 meters, which is typical for the Alps, then we can imagine that at L-band, if we have a penetration of 20 meters, of course I see the ground below. Or I have even penetration into the glacier and the fern area below, because typical 2-3 meters, if we are lucky 4 meters, it would be an excellent winter in the Alps. Then at C-band, we still have a one-way penetration, so we have to divide it by 2 in order to get it both ways, because we are looking to backscatter. So we are in the order of 1, 2, 3, 4 meters. So we still have a lot of information, not only on the snow itself, as long as the snow is dry, but also from the ground below. And therefore, as I mentioned below, the conditions of the ground are super important. And if we go to higher frequency, the smaller this penetration length will be. And of course, it has also an impact what we are seeing finally in the radar image. A super simplified model to see how a snowpack could look like. We have a snow depth, ds, then we have a kind of transmissivity, tau s. I'm not going to the parameters, but it should explain you how a signal which is measured by the satellite, which processes of backscatter are important. And this is now for dry snow. So we have a snowpack in the order of, let's say, 2 meters, 1 meter. Then, of course, I have when the radar transmits the wave, then it hits at the first, okay, it goes through the atmosphere and so on, and then it hits first the snow-air interface. That's the first process. It's a kind of surface scattering process. Then some parts are a little bit is reflected in some of the directions, and other parts are going into the medium, into the volume. We assume here we have one very homogeneous snow layer distributed and characterized by these parameters, what I have mentioned before, so uniform density and so on. And then, of course, I have the grains in there. And these grains are scattering. Okay, they are interacting, the wave passes through, and the more grains I have, the stronger is the volume scattering. In principle, I come later to this. This is a very, very simplified view. And then finally, the wave penetrates through this snowpack, and finally it hits the snow-ground interface. So therefore, it's important what is the permittivity difference between the snow, the dry snow, and the ground below. What are the ground conditions? Therefore, we are looking to this. And this is the third component. So in principle, 3 components: snow-air, volume, and snow-ground interface. These are the major contributions. You can model this. Okay, I'm not going to the model part. But of course, when we are looking, when we want to get information on the snow height, for example, or on the snow water equivalent, I'm interested in different process of the scattering. Snow volume, for example, information on the snow volume, I'm primarily interested what goes on in the scattering part within this volume. So the scattering on the grains, on the layers. But when you compare it, this super simple model with what I have shown before, we have layering. Every layer has a different density. Every layer might have different grain sizes, grain structure, and so on. So it's much more complicated. But to understand the physical basics, just remember these few and say, okay, I know the basic principle, but in reality it's much more complicated. And it gets even more complicated. When we look now to the volume scattering part, I mentioned before that we have here these single grains in there, and they scatter independently. This is very simple to describe, but this is not the case, I can tell you, because snow is a dense medium from this point of view. So near-field effects between the scattering parts are important, and there is an overlay. So in principle, we have to take this dense medium effect into account. It's not so easy because, again, we need some kind of model. And super clever people from Seattle, so Zhang, for example, or Chang, they developed a couple of models, actually, with are describing mathematically this dense medium effect. One of these, what they use, is actually this quasi-crystalline approximation, which is very nice. It gives you the impact when you have this sintered natural snowpack, which is clustering together different grains. Then you can actually have a parameter which describes you the lowering of the interferences of the scattering of the different grains, and this is the dense medium effect. But this is still a model, we have to say. And they invented super parameters, and one of those is, for example, the stickiness parameter. I never measured it. I didn't see it, actually. But you can use it in your electrodynamical model, which is why it's complicated, as a parameter to tune actually the model, this dense medium effect, to your measurements to understand it. But of course, measuring a kind of stickiness parameter is probably not so easy. What is needed now for a very basic radiative transfer approach in order to start with the modeling? You need an effective grain size. What is an effective grain size? It's not what I have shown before, because that's what we are measuring. Effective is what the radar or the microwaves are actually seeing. And you take a kind of approximations. How do you get to this effective? So I personally do it in a very simple way. I have some measurements, and I have the model. Then I fix everything what I can measure, and then actually I adjust the grain size in a way, very simple, that the model can explain the incidence angle dependence of your scattering, what you see. Then you need a scattering phase function and a kind of dense medium parameterization. One of those is the stickiness parameters. If you take, for example, 0.1, depending on the frequency, you can look this up in various literature. It's a very good approximation. So this works very nice. That's the experience what we have from very many validation experiments. Now, you see here, actually, now when we are trying to understand where is from a complete, and this is now the backscatter at VV polarization, HH is very, very similar. Independence on the frequency. We have the total backscatter here as the full line. Then we have the backscatter from the snow volume, and we have the backscatter from the ground. So it's written here soil, but from the ground snow interface. Air snow interface is in general not mentioned because this contribution is super small as long as the snow is dry and not super rough. But if you have this nice winter snowpack, then this is a super small contribution. And you see in principle that snow-ground interface, the snow-ground part is important, especially at the lower frequencies. The higher the frequencies are becoming, the volume plays a role. I put this slide here for a summary for you, that's for taking home. So dry seasonal snow. That's the dominant mechanism, is scattering in the volume, and that is no ground interface. If you try, there are public models, so there's the SMRT model around. You can actually download it. It's on GitHub. So she's learned, actually, it's written in Python. There are Jupyter notebooks where you can play around with the different parameters. You can set up your snowpack with the different parameters, and then you get these curves, what I have shown before, so very nicely. But the dominant scattering is for the dry seasonal snow. What we are primarily talking here is scattering in the volume and snow-ground interface. Then we have microstructure, so grains and this sintering and these effects are especially important when we go to higher frequency. Therefore, when we look to new satellite missions looking for backscatter retrieval, they are working at KU bands, so 17 gigahertz, or sometimes even higher. Then for snow mass and snow water equivalent SWE, what is, I would say, the holy grail in snow to get this, to measure this, we have a low sensitivity of backscatter in the range from L band, C band, X band, a little bit, but Q band is quite sensitive to this. But the problem is here the microstructure of the snow, and this starts to playing a role when I go to higher frequencies. We are in the range of a few millimeters wavelength, and of course, bigger grains, clusters, they have the same size, and if the size is in the same order of magnitude as the wavelength, then this plays a role. For wet snow, the dominant mechanism is surface and volume scattering. I come to this tomorrow in a little bit more detail, so I just let you know. For wet snow, it's totally different. You don't see normally the volume very much. It's primarily surface scattering of the air-snow interface. So penetration is in the order of a few centimeters, a wavelength or something like this. And then for the percolation zones, because I thought I put this also in, some glacier people are here looking at this. Percolation zones, we have big grains, of course, and they have a big volume scattering contributions. So the primary or dominant mechanism is volume scattering in this case. Therefore, this percolation zones is in general, when you look to a radar image and this zone is dry, it's a very bright zone. It's not only that the volume plays a role, but also we have internal interfaces between the different snow layers and different densities. And it's also a kind of complex medium because the layering of these percolation zones is quite different from a natural alpine snowpack. Okay, as a summary. Now, what can we do with these measurements? How can we retrieve snow water equivalent? So, of course, there are many ideas around. Maybe you have your own one. So it's very good that you work on this. I show you what has been done so far. Let's assume we have a dual frequency SAR in space. Core H2O was a candidate mission for this, working at X and KU band, at Cross and Copole. And we had 4 independent measurements at these 2 frequencies. But how can we retrieve snow water equivalent out of this? So the approach, what we selected or proposed, and it's also used now in principle very similar for this new Canadian mission, which is coming up. I talk about this later. We use a kind of cost function. We need a model. So the first part is the forward model. I wrote it on top of this. That's a model. The equation below you see. We use a super simple model in this case. Okay, you can make it very complex. In this case, it's a simple one. And then I have the measurement, okay? And in principle, I fix everything what I want to fix and have 2 parameters of freedom. So this is the snow water equivalent. And what is also important is grain size. And then I'm optimizing the model in a way, only with these 2 free parameters, iteratively, that it matches the measurement. So imagine you have the satellite passing over, measuring this image. You get 4 values per pixel, and then you start with this retrieval. You have an idea, but it's not working that simple, because here we have a regularization. We needed this. We need a first guess idea in order to retrieve it. So we need to know, otherwise it could go somewhere, this iteration. Okay, if you let it just run and hope for it, it goes somewhere, but we have an idea how much it is. And for this, we are using a regularization, and we can take this from different other information. For example, I know a grain size is approximately this size. Not accurately, but maybe we assume 1 millimeter. It can be a little bit less or a little bit more. But this should be then tuned actually for by this iterative process, that the model, if it fits to the data, it runs iteratively, and then I stop at a certain when there is no change anymore in the modeled minus the part. So a kind of cost function part. And this was actually developed for core H2O, and I show what it brings you. So it's, we tested this, of course, with the many data. So SNOWSCAT was a scatterometer in Sydankila. Sydankila is in North Finland, very close to the Russian border. It's an Arctic research center operated by Finnish Met Office, and they have installed these very nice measurement sites. Not only we did our measurements there are many other measurements. So there is L-band passive microwave, and so different instruments are installed on this tower. You see there are these big, the big antenna is a passive microwave instrument in preparation also of a satellite mission. And they are doing there, of course, also regularly in situ data measurements in order to fix it. And actually what we got there is a kind of what we would have got from core H2O. So there were two campaigns in 2009 and 10, NOSREX 1 and NOSREX 2. And you see how the data are actually looking like. So it's a KU band, it's 17 gigahertz, it's a small frequency, it interacts a lot with the volume. Therefore, we have a relatively high backscatter. X-band is a little bit lower. It's 9.6 gigahertz, what we used here. And we did this for 2 winters to be a little bit more independent. And when we are actually running the algorithm, what I have presented before, we took some measurements actually to have these regularization values, so some starting values. And then you see it more or less matches the line. Okay, it's not always the case, I have to say, but I selected a nice example, of course. And so in red, you see the snow water equivalent, what was retrieved by the observations. And then the best guess values here as a green line. Best guess SWE, because in the first winter, they did not measure snow water equivalent. They had no automatic station there doing this. So in the second winter, people went there and measured it by hand every week or 10 days. So these are these big green dots there. Best guess is that we had a kind of guess of the density, and we had this ultrasonic in order to measure the snow height, and this was then converted to snow water equivalent. But in principle, it matches quite well. We have, of course, some differences in some of the parts. This could be that we are not taking into account properly ground snow interfaces or the grain size. But in principle, it's quite a good result, I would say. This was on one point from the tower, and then we had an airborne campaign doing the same in principle to see actually if we can generate a map. So this is needed actually in order to prepare the satellite missions. And this is a kind of map where we blend, so we go to the simple side. So it was in principle a horizontal meadow where we flew a couple of times there. And finally, when we look to these snow water equivalent measurements and the SWE from the in situ measurements, so there were 20, 30 people in the field parallel to the flight in order to make many snow pits so that we have enough samples in order to see also the spatial variability on the ground and if we can catch this actually by the SAR. And the agreement, I would say, is quite reasonable. And if you want to need more, so this was published by the core H2O team in 2010 in one of the ESA reports. And we used actually here the two SWE and the effective grain size as a free variables, and we took this also for the regularization. So that's definitely something what is needed. Now, KU band is interesting. So that we found out before core H2O, there were very, very sparse KU band measurements available. And core H2O was not selected as an Earth Explorer, so biomass, which is launched now in April next year probably, was preferred against the SNOW mission. But research actually continued. And especially the Canadians actually, they set up in the SNOWX campaigns a couple of measurements also with KU band. And this is and we were primarily interested on this interaction of the microwaves with the snow volume, so with the grains, because this was not, or is still not fully explored. And you see here 1st of March and 3rd of March in 23, so last year, they did a kind of experiment to see how strong is the real impact when, for example, when snow is present. And we did a super simple experiment. We just removed the snow in the second flight. So you see it here. A field of, I don't know, was it 20 times 20 meters? This complete snow was removed as good as possible. And then we intercompare actually the impact of this reversal of the reversed snowfall. And when we look to this, I show you here, so it's in the brightness image, you clearly see that there is a big change in the backscatter, and the change is really strong. So for this 64 centimeters of snow, 45 centimeters of snow, and 42 centimeters of snow, the change was from minus 9.9 dB to minus 14.6 dB, averaged over very many pixels. And then, of course, also with 45 centimeters, it's also about 7 dB change, and a little bit more even for the 64, which is actually expected. So what we see here, a super simple experiment, Ku band is an excellent frequency for this. And this was one of the motivations actually to define a kind of terrestrial snow mass mission. This is still under evaluation by the Canadians. It's a dual frequency mission at Ku band, operating at 13 and 17 gigahertz, providing VV and VH, very similar to core H2O. But core H2O had X and Ku band, so high Ku band and 70 gigahertz. This is using only 13 and 17 gigahertz. Then it has an option for SAR interferometry, as well with of about 500 kilometers. The aim is not to go to the mountain regions, but primarily to look for flatter terrains in order to get high resolutions of 500-meter observations of snowwater equivalent. And there is, of course, a lot of information going on when we are looking to this dependency of VV and VH in 13 and in this case 16 gigahertz. We see quite nicely that first the models are more or less correct now, so we can model this part, so the cost function approach can be applied, and that we have a very nice relationship between the backscatter and the increase of snowwater equivalent. So this is really a very interesting approach. And we hope that the mission goes on, of course, because that would be really a big step forward. Let's go to Sentinel-1. That's also interesting. Can we use Sentinel-1 actually to look for snow parameters? So here, and I'm focusing here now on the backscatter part. And I would say what I show here is one location in Wattenerizum. So this is a research test area of the Austrian Avalanche Service, Research Service, and they are doing their regular in situ measurements on the snow pit, snow information, ground information. They have an automatic station there, an automatic weather station there, and therefore it's very good, of course, because of this very dense time series of observation in order to look what is possible. So that's the first site, and in the upper part we see here the time series of snow depth. Actually on this place, close to this place, what is here on the photograph. And we are having up to about 1.5 meters of snow typically there, but it changes, of course, from winter to winter. So we're starting here in winter 17 to winter 21. And then we have a dense time series of Sentinel-1 images every 6 days. First, to observe it from different observation directions, so ascending and descending tracks, at the typical incidence angle, and we were calibrating this to sigma naught. And you see here in orange the VH one, which is rather low. Then the VV is in blue, and the difference between VH and VV is the red curve. When we intercompare it now, more or less, on the time series, so in the first, in the first winter, so we have about 1.5 meters of snow. There's a decrease actually of VH, VV. VV increases slightly and VH stays more or less constant during the period. We have a very strong signal when there is a melt. But we have to be also careful when we are interpreting this data, because the noise equivalent sigma 0 of Sentinel-1 is minus 25 dB. So when there is a melt, actually, backscatter drops off dramatically. but the system itself stops at about minus 25 dB, depending a little bit where we are in the swath, so it's changing, it depends on the antenna pattern, but there's a number, you can say minus 25. It cannot go below minus 25. So, but on the other hand, because what you're measuring at this very low backscatter is primarily thermal noise of the system. So this is called noise equivalent sigma 0. It's a system parameter actually, what you specify when you design the machine. And of course, when we look, for example, for VV, this goes much more down than the VH, so the cross pole. So we have to keep this in mind, and therefore there is this peak here when we make the difference. But it's not necessarily caused by the physics. It might be a kind of measurement issue. And then, of course, when we go to the second winter, it's a small impact again. At the other winter, it's again a small impact, even a decrease of this one. And here it is slightly different. Let's go to a different point very close to this. And then I explain you the problem. We have only 3 winters. We go now, so we were here doing the measurements before, and then we go up very close to this, to the Downthaler bone, 500 meters higher in elevation, a little bit oriented towards a different place. We were also there doing measurements. And then when we look to this time series, then we see, for the first winter actually, we see a 3 dB increase of this polarization difference. So it seems actually that on this side, there we have an increase, so a signal which looks or looks like that it has an impact by the snow depth. On the winter afterwards, it's a little bit less. I would say when the snow starts, so this is before it gets wet, we have it more or less no impact, then it's a jump up, and then it goes even down again, although there was no change in the snow height. And when we go to the third winter, there is no impact. Very tricky, actually, to understand this. And what we did is that for these 2 sites, we were looking for snow depth versus this gradient in the polarization, and look for the trend. And when you see, for the zoom in the same year, just a little bit apart from each other, we have a negative trend for VV, and in this case, and the polarization difference is going down. On Downthaler bone, the same is going up. A year later, there is no impact. It's more or less a horizontal line. While on Downthaler bone, which is obviously for this method the better side, we have an increase. So what does this mean when we want to exploit C-band data for measuring this? That there is obviously, and we know this from the measurements, there are differences in the morphology of the snow, of the metamorphosis of the grains, and also of the conditions of the ground below. So this is important to understand. It's not that C-band is not interacting with the snow. There's some interaction, but it heavily depends on the snow conditions, even if they are bad. And this makes it hard to make a retrieval algorithm, because we need to know what's going on there. So it depends also when the snow is coming. So we need to understand the physics behind it. And so in principle, what we need to know, okay, for Downthaler bone, for 1 year, for example, in general, it looks like that you can design an algorithm with an increase of this cross-pole to co-pole. You can actually have a very nice algorithm. But you go 500 meters or 1 kilometer next to it, it's totally different. Because as I showed you at the beginning, snow is not always the same, does not have always the same conditions. So also the ground conditions and how they change during the season, this is important. And that makes it complicated. Okay, I change now the method. I like the face, so it is very, this is, I think, for me, this is a very, very promising part. And so John gave you, I think, a very excellent introduction on SAR interferometry. And we use the same signal now, so the phase difference between 2 dates, in order to look for what can we do with snow. So in 2001, Gunnar Rissen from Norway, actually from Norway, he published a paper with 1 data set of ERS where he said, okay, there is some relation between the phase and the snow water equivalent. And okay, you read this, we tried it also, but ERS had 35 days repeat cycle, It's very long, actually. In the Alps, to test it 35 days, a lot of things can happen. So in general, we were losing coherence. But during one of these preparation campaigns for Core H2O, we had Keith Morrison in Innsbruck with his cherry picker radar. So it was a very nice instrument. So it was a SAR system. You see here the rail, and that was a network analyzer, and then somewhere we had here the power supply. And you can move somewhere to a field, somewhere in the Alps, just pick it up. After 2 hours, you set it up, and then you can do some measurements. And at the end of a long day, we actually, so it was almost dark, we said, okay, we test this now. We had the idea, just we make, and this was actually in 2007, we went to this a place just below in Kütai. We went there, did the measurement with the natural snowpack. Then we were removing by hand, not with a truck or whatever, the snow. And then we said, made a measurement again, and then we applied interferometry. The aim was to see, is there an impact? Do we see something? Okay, just very quickly. We see something very strong. What we see is, and that was X-band, because we had only X and Q-band, and then as we even see in Q-band, but here I show the X-band. We see very nicely a phase jump, very good. And we see even when so this part, we were throwing out the snow from the part. So we see this, and the phase was in the right direction. So this we were actually confident, okay, this works. And the nice thing on this is, when we do a little bit of physics, it's independent on grain size. It is independent on the layering. It is independent on a little bit dependent on the ground conditions, but not so much. And of course, it's nothing always good, I have to say. Unfortunately, you need coherence. At that time, we wanted to go on with this 35 days, and we thought ERS, we didn't have the right tools in space in order to test it. But now these tools are coming, so 15 years later. How does this method work? Yeah, that's the method. John introduced all of this. We are measuring the interferometric phase, okay? Then we have a contribution of the phase due to the flat Earth. That is because the radar is going like this, but without topography. Then I have a DEM. This is this topo. So a contribution also because we have height changes also in range. If I have a DEM, both I can calculate accurately enough. Then I have some contributions of the atmosphere because I have two dates. Date 1 and 6 days later, atmosphere will change, especially water vapor. I have a phase screen on that. It's not nice because we need an external information on this, but in principle we can calculate this. And if I can correct all of this part, I get the phase change, interferometric phase change due to snow accumulation between two dates. It's not the absolute snow water equivalent, it's the snow water equivalent between the two dates of the measurements. So it's also clear there are some limitations. When I go for a whole winter season, I need a continuous time series all the time. But this is to be done. Now I can model this. I'm not going through the equation. So here it is snow height, and that is the permittivity. Cosine from E is the incidence angle, which I know also accurately. I need also the slope, which I did not put in there, but I know it from the DEM. Then for epsilon, this for dry snow, this depends on the density only. So I need an estimation of the density. But when I do some mathematics and a little bit some approximations, and using that the change of SWE is the change in snow height times the bulk density of this one, I can get to an equation like this. There are different equations, approximations around, but it's a direct relation between the change of snow water equivalent and the measured interferometric phase. And this is very nice. No grain size, no other issues which are nasty. So in principle, this is quite nice. What I need is, when I do it actually, is a kind of reference phase. I need to know, because phase is, I need a calibration point, so that I say on this point, this phase has no or a certain amount of change of SWE. This I need. Okay, how sensitive is this? It is super sensitive. So we like large wavelengths. So this is one phase cycle, so one fringe. When you look, for example, for ice velocity, you have many fringes. So one fringe, actually, so one phase cycle corresponds, I show it here for L and C band and S band, independence on the incidence angle, so it depends on how I'm penetrating through the snow. 40 degrees, typical from Sentinel-1 or from upcoming L band missions. So one phase cycle is about 1.2 meters of snow, if it's fresh snow with a density of 100 millimeters, or 120 millimeters of snow water equivalent. At C band it is 28 millimeters. It's only actually, if it's fresh snow, it's like this, so it's super small. When you remember the snowfall, we had 1.5 meters in 1 day or 2 days up at Hintertux yesterday. We would have many fringes at C band. L band is the way to go because it is more appropriate to this measurement. At higher densities, for example, it's 9 centimeters at C band. It is super small. So when you have some snowfall, let's say 20, 30 centimeters, you have to phase unwrap this, and this is nasty. And sometimes this is for a large phase plane, you need a reference point, and you have to unwrap the phases, makes it more complicated. When we look a little bit to these approximations, we see up to 40 or even 45 degrees, we have no density dependence. So this is very nice. So this is now the different for, again, for L band with SWE of 20 millimeters, assuming a density in the correct formula of from 0.1, so fresh snow, to very, 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 very dense snow. This is the correct application. These are the different approximations. And we see everything is more or less the same below 40, 45 degrees incidence angle. Very nice, and need not to take care on the density. There is another approximation where you can even go further, but this is the more simple one to show. That's very nice, because then we have really a direct relation between snow water equivalent and the phase, more or less independent on the density, grain size, and all of this part. And that's, of course, very nice to have. So, some results on this. We did this, we started again from the ground, and one issue is coherence. So actually, when we go to this, we see that we have 12 hours, 4 hours, and 7 days. We see C band decorrelates after 7 days. L band is much better. So L band actually, even after 7 days, we can follow more or less the line. Rose L will have 2 satellites in space, 6 days apart, acquisitions. It matches more or less this SWE accumulation, what we have shown here. Temporal decorrelation is the main issue for this technique. How do we process this? So this, I will not go into detail. So this is a kind of flow chart, just to see what you have to do when you want to implement it. We start with the 2 SAR images on the day, then we run the standard interferometric processing, everything what John explained in detail. We have to correct for the topography. We need some numerical weather grids in order to remove the atmosphere. Then I get the interferometric phase due to SWE changes. We might have to phase unrip if there was a big snowfall. If there was a smaller one, it's not necessary. What I need to have is actually a reference point for every phase plane. So if you don't have a continuous phase over the complete image and some patches around, you will see an example, then you need a point to calibrate the phase to know this phase value at this point corresponds to this delta SWE. So the best would be a 0 point. So without any change. If we have high incidence angles, we need an idea on the snow density. On the Alps, for example, on back slopes, you might have incidence angles of 60, 70 degrees. This is the case. We take this from models. So snowpack models are running over the Alps, for example, over many places. You need just a rough estimation. It's not that sensitive. A rough estimation would be very helpful. If I would not have any information on this, I assume 150 kilograms per cubic meter. That's excellent for fresh snow, because snow is not falling as an ice block, so it's fresh snow. We know it's between 100, 180, something like this. So with 150, it's a good number, if you don't have any other information. If you have other information, you can use regional climate models or whatever in order to use it. And finally, you need some land surface types. Forests is not so nice. At L band, we will see that you have some phase information, but the snow is a little bit masked. And finally, if you apply this, you get a map of delta SWE. From the practical point of view, we are not doing this continuously over the season, but not every day. We will not get the data. We will combine it with the snowpack model, which gives you the temporal resolution. Snowpack models the snow accumulation relies on the precipitation. Precipitation in the Alps are wrong or not accurate enough. And now if I get an update of the amount of snow water equivalent every week, I can update the snowpack model and bring it back to reality, which is a big step forward. So that would be the application when you go towards an operational one. We did some information here in Bergetal, a campaign, but I have to hurry up now. Otherwise, I take a few minutes from your coffee break. But you drank a lot of wine yesterday, so you can, can do this. We had a campaign there to prove this. We had 9 flights, also in Kütai. It's a higher Alpine valley, a very nice ski for ski touring. And you see here 3 circles actually where we were doing intense observations during the DLR overflights at sea and L-band. And we had in this period, in March, I think 21 or 22, we had 2 snowfalls, and before and afterwards we had flights. So the first snowfall was about 5-6 centimeters all over the region, and the other one was about 30 to 50 centimeters. So at lower parts a little bit less, at higher parts a little bit more. So this is unterer Boden, so medium, and the upper one. Okay, so that's 2,400 meters, 2,200, 2,000 meters approximately. This is the coherence. C-band works for the small part, and L-band works for the small snowfall, so 5-10 centimeters. For the moderate snowfall, up to 30-50 centimeters, C-band fails. L-band works quite nicely. So therefore, we are going for the L-band for the satellite data, because 50 centimeters of snowfall is typically within a few days. What were we getting out? Just as a very quick summary, we have here the snow water equivalent. So these are the measurements in gray. Then there we have observations from both directions, and we intercompared this at L-band in bluish colors here from one direction, and these yellow colors here from the other one in HH and VV. So polarization difference is almost none there. Also for the higher snowfall, we see a very good agreement here. And then at C-band, only the small snowfall phase. But in principle, we see that obviously one look direction is a little bit better than the other one. It could be that this is an incidence angle effect which was not properly corrected in our processing. So you see here the difference between the retrieved and in situ measurements. I would say this would be a very excellent result if you can get this over the Alps and provide this to the people. Now to Sentinel-1. We tried it, of course. A lot of images. I show you one example. So this is, you don't know the region. So this is Chur, so in Switzerland. Samedan, so that's Engadin, so this part. I selected 2 images, processed one with the big snowfall. This is this one in this region here. And that with the smaller snowfall, this is this one here. So it's approximately 100 meter pixel spacing. So we multi-looked it, 20 pixel in range and azimuth. Some critical issues were the removal of the atmospheric phase, because we used error 5 for this, and the resolution of this model is definitely not the best in alpine regions. And also the selection of the reference points is quite tricky when you want to apply it, because for each of these isolated phase planes where you have coherence, you would need a point, and in high alpine terrain, this is not so easy to find actually, because you don't know it. So this is still some question. For the higher snowfall, in principle, I would not touch this data. You can forget it. L-band. So this, we did not get excellent L-band data. It is 14 days apart. We see here the coherence image. So there was some, actually, so this is the coherence between blue, so dark blue is 0, and 1 is white. Here was a lot of snowfall in this region. In the south here, so Lago di Como and so on, there was absolutely no precipitation, no snowfall at all. Therefore, coherence is high. It is a 2 weeks interferogram. It's quite long. So normally, L-band pulsar is acquiring every second cycle, so 28 days. For the Alps, impossible, I would say, because there is so much meteorology going on. Weather systems are melting up to 3,000 meters, refreezing again. This is too much. SAR, which will be launched actually in February, will provide, hopefully, will provide 12 days repeat intervals, which is much better, approximately like this. Roselle with 2 satellites coming in 29, hopefully, so before my retirement, hopefully, I hope so. Then this will be 6 days repeat. And that, I think, what we have known, what we know from the field or from the ground-based measurements, that's the system what is really, really promising to look at. But for this data set, we look to one example, a kind of prototype product, how this works out. So this would be the INSAR retrieved change of snow water equivalent between these 2 days. So this is the beginning of February, 2 weeks. The color code is here, so this yellow is 0 up to 30 meters. We took actually a station here at Maloja at this pass, and then we intercompared it with a few of these measurements. It was COVID time, so we couldn't go there for doing more measurements, so we had to rely on this. But it shows in principle that we can repeat a little bit this accumulation of this in this time frame. And, but of course, a full validation of such a scene is still pending. I have 2 more methods, so you have to give me a few minutes more. Single pass INSAR will be very quick. That's now a new method, what we try. So we have tandem X in space. What we try actually to develop to measure directly snow water equivalent and or the snow depth. The basic approach is super simple. You acquire 2 single pass interferograms like tandem X, make a DM and subtract the DM. Sounds super simple with LiDAR. This is straightforward to do. But can we do it also with radar? What we need is some corrections for the snow density. I will not go into detail here, but just that you know it. But there are some critical issues here. First, we need a very accurate processing of the DM generation, much more accurate than it's currently done at the standard tandem X process, and I'll show an example later. Then signal penetration in dry snow, we know it's passing by. Okay, but we can choose the right snow conditions. We know at wet snow, you will learn it tomorrow, there will be no penetration, so we are at the top. Another option would be change the system, go to a different frequency. And I show a very promising example here. And then for foreshortening and layover, this is just, you need the data, you need both look direction in order to get the coverage. That's an example here, how it works. So we have here tandem X data, bistatic, no atmospheric influence, because both images are required at the same time, so we need not to correct for the atmosphere. One problem is when we look for the wet snow, that the noise equivalent sigma 0 of the system is -21. At X band we can go below, and then of course the phase noise is high. We have to take this also into account. And then of course I need this calibration and the penetration bias compensation if needed. But this is still in development, that's not an easy task. And we can apply the DM, and you see how this looks like. We tried this, a couple of people tried it with standard tandem data, and the outcome was, no, it's not suitable. You need a better processing, and actually together with DLR, we developed a procedure which combines permanent scattering of stable points of Sentinel-1 in order to correct the orbits and the phase plane of tandem X. So to remove the baseline error which is present in the data, and this is shown in this graph. So this is a small phase plane of the complete scene of 30 kilometers times 100 kilometers. So it's, this variation is about 2 meters. So over the complete plane you have a small trend, and this causes, if this is not corrected, you will have a tilt over one of the DMs. And if you are not correcting it, of course you will have 1.5 meters shift, and this is actually the signal what we want to observe. So because a typical snow height in alpine terrain is 1, 2, 3 meters, so we are in the order of magnitude. So we are actually looking for time points in the Sentinel-1 images. Why we are using Sentinel-1? Because we have a long time series, and I can identify from the long time series the stable points. With tandem X I don't have the time series. So the basic idea is I select the Sentinel-1, identify the stable points, so big boulders and houses or which are really stable in time. I can do this directly from the data and look for these points in the tandem X data and correct then the tandem X data. It's not so easy. There is some assumptions are needed because stable points are frequency dependent. But actually, we found quite a good method in order to calibrate finally this tandem X data. And when you look here, for example, for the difference, so tandem 1, the DM1, DM2, and the calibration plane, then we can look here for some profiles. If it's uncalibrated, then we see that we have the difference calibrated with the offset, and then with the standard offset. And then if we look for actually this correction with the plane, this is more or less the same for a terrain which is not changing. We try to measure actually, yeah, it's a challenging. We try to measure snow depth from the Aletsch Glacier. There is one station we took the Aletsch Glacier because it was a flat terrain. We had the station there. We knew the terrain. It's easy to go there. We had only 2 images. It's tandem X, so we don't have this 6 days time series. So it's just a kind of idea what is exploiting. And finally, when we apply all these corrections, we use the reference DEM. So where we say, okay, there is no snow. We need the kind of snow-free case. That was in November. There should be no penetration in this. It is not so easy to find the right reference data if you have a sparse acquisition scenario. If you don't have the time series, it's not so easy to do this. But finally, we managed to go to a delta of the observed versus the in situ measurement of 30 centimeters or 78 centimeters. It's much better than what was before, but it's not actually good enough, I would say. If you have 1.5 or 2 meters of snow, 30 centimeters, 10 centimeters would be quite good. But that's what we can do so far. We are not at the end of the story, so this is still going on, the processing. And to correct for this, and primarily what we need is to get the right data at the right time to avoid penetration of the reference DM and also penetration in those DMs, so to look only for this wet snow part. But there's another idea. So we are going now the same technique, but we switch actually to K8 band, so 35 gigahertz, super small antennas, small wavelength. And when we look to the penetration here, we have almost no penetration into the wet snow. It's super accurate. And this is now an instrument which was flying on the NASA G3 aircraft. So the instrument is just there. K8 band has the advantage, antennas are this size. It's all nice. So L band is super big. K8 band is super small. It's very handy. Everything fits into this small part, actually, including antennas and everything. And they run this instrument there over in the US, in Sierra Nevada, and compared it actually with the airborne LiDAR scanning on the same plane. And the agreement is really nice. So when you look here now to the differences, independent, so facing towards the radar or opposite of the radar, we have an accuracy or agreement with the LiDAR change, LiDAR derived snow depth in the order of centimeters. So this is actually something what is there. And there was a mission proposed called Signal, which was also not selected, but this is on the way. So ideas are around in order to bring this in space. This was just in the last Earth Explorer call. And finally, the last method, it's SAR tomography. It's the next step of processing from SAR interferometry. So we are not looking, so SAR provides you a pixel, while tomography, in principle, provides you information on the volume. It's the same as in the medical sciences, we're using MRT or CT, so we are looking from different incidence angles to the space. And there is, I can promise you currently there is no satellite mission available, but ideas are around. And we did actually some experiment also in Rotmoostal at this field campaign, where we set up a radar system and measuring on different, so this beam was at different elevations looking to the same site, and in parallel we did in situ measurements, and to see can we retrieve actually the snow height out of this, or even get information on the layering within the volume, which is also very interesting. And the snow depth retrieval, so what we know so far from a couple of field campaigns, is very accurate. So we have one acquisition, so no temporal decorrelation. So we need 3 or 4 instruments in space actually to observe this. And finally, we can retrieve the snow height by looking to the snow ground interface minus the snow air interface, just the difference of the tomography in order to estimate this. And the accuracy would be in the order of a few centimeters. And that's, of course, a very, very accurate system. And this is the final slide, that we have the outcome of one of these experiments, what we did. There are more experiments around. So you see the instrument was up here, so we see here the ground range, so the distance on the ground from the radar. And then you see the different backscatter layers here. So these are internal layers. And then there's the air snow interface here, and also the ground snow interface, this part. And then, of course, when you're just interested on the snow height, you just subtract this from each other and would get at the same time this information. This is something what people are currently working on this. And yes, I think this is my last slide. I gave you here also some references when you get the PDF. So it's a lot to read. If you need more, just contact me. But I think this is a very good introduction. Not everything, I would say, is solved so far, but you see now where we are going, in which direction, what are the possibilities. So it's not only one method, what is the favorite. So depending on the snow situations, we can select the right method. And okay, so thanks for the few minutes more. Questions? Anybody? Okay, if not, then we go to the coffee. Thanks.